Today, we are going to pull back the curtain on maybe the single most important invention of our time, the CPU, the Central Processing Unit. It's the silent, invisible engine running our entire digital lives, and its origin story, well, it's one of the most incredible feats of engineering you can possibly imagine.
So let's just start with a simple question. You look at a pile of ordinary sand, right? And then you look at your computer, one of the most complex things humans have ever built. What could those two things possibly have in common?
The short answer? Just about everything. It sounds impossible, but that little supercomputer in your hand or on your desk, it started its life as simple, humble sand. And we're going to walk through exactly how that happens.
But okay, before we get into the mind-blowing manufacturing, let's just get on the same page about what a CPU actually is.
A CPU is basically the part of the computer that gets things done. Think of it like it has three main departments. You've got the control unit, which is like the project manager, directing the flow of information. Then you have the arithmetic logic unit, or ALU. That's your math whiz, doing all the calculations. And finally, you have registers, which are like little super fast sticky notes for holding on to whatever the CPU is working on at that exact moment.
Really, the best way to think about it, just like Lenovo says here, is that the CPU is the brain of the whole operation. Every single time you click your mouse, type a letter, or do anything at all, that command goes straight to the brain to be processed.
So, how does this brain actually do its thinking? It's not some kind of magic. It's actually a cycle, a super fast and precise cycle. At its very core, a CPU just does four things over and over again: fetch, decode, execute, and store. It grabs an instruction, the control unit figures out what it means, the ALU does the math or the logic, and then the result gets saved. Simple, right? Now here's the crazy part. Imagine that cycle happening billions of times every single second. That's the mind-boggling speed we're dealing with here.
Okay, we know what it does. Now for the truly wild part. How in the world do we build something like that? We're about to go from the clean world of digital logic to the gritty physical reality of manufacturing.
And yes, it really does all start with sand. But this isn't beach sand. This sand is purified to a level that is almost impossible to comprehend. We're talking less than one rogue atom for every billion silicon atoms. This ultra-pure silicon is then melted down and grown into this perfect single-crystal cylinder called an ingot, which weighs about 100 kilograms. They take that massive, perfect crystal and slice it into these super thin discs, only about a millimeter thick. These are called wafers. And they get polished until they are smoother and more perfect than any mirror you've ever seen. Each one of these will become the foundation for hundreds of CPUs. And now for the real magic, photolithography. You basically coat the wafer with a light-sensitive material. And then you shine ultraviolet light through a stencil or a mask that has the circuit design on it. It's like photography, but on a microscopic scale, printing these unbelievably intricate patterns onto the silicon. After the pattern is printed, chemicals are used to literally etch away the parts you don't need. And this isn't just scraping off a layer. You're sculpting the silicon itself into tiny three-dimensional structures. These little ridges you see are called fins, and they're going to become a key part of the transistors, the little on-off switches that are the heart of all computers.
So, how many of these transistors are we talking about? This whole process is repeated layer after layer after layer to build, well, literally hundreds of billions of them on just one of those wafers. The scale is just staggering.
So once you have billions of transistors, you have to connect them all together, right? That's done by adding more than 30 layers of metal wiring. It creates this unbelievably complex 3D superhighway that lets all those billions of transistors talk to each other at the speed of light.
So we've built our city of transistors. Now, let's talk about what actually makes one CPU faster than another, because it's about more than just cramming in more and more transistors. First up, you've got cores. A core is pretty much a single processing unit, a brain. Old CPUs just had one, but modern CPUs have multiple cores, which means the chip can literally work on several different tasks at the exact same time. It's what makes multitasking possible.
Now, if the cores are the brains, then threads are the individual trains of thought. A program will break its work down into these threads. A CPU with multiple cores can then give different threads to different cores, letting it work in parallel to get things done way faster.
Then you've got something called cache. Think of this as the CPU's own personal super-fast short-term memory.
It's a small bit of memory located right there on the chip itself. It stores data that's being used all the time, so the CPU doesn't have to waste time going all the way out to the main system memory to get it. It's a huge speed boost.
And finally, there's the basic design philosophy. You have CISC processors, which are built to handle really complex tasks in a single step, and you have RISC processors, which use much simpler, faster instructions. It's kind of like the difference between a Swiss Army knife that does everything and a set of specialized high-speed tools. You'll usually find CISC in desktops, while the power efficiency of RISC makes it perfect for our phones.
All right, we've gone through the manufacturing, the architecture. Let's zoom back out and see how this incredible patterned wafer becomes an actual product you can hold in your hand. There were really 3 last big steps. First, every single one of those hundreds of chips on the wafer gets tested. Then, a diamond saw slices the wafer up into individual chips, which are called die. And finally, the good die that passed all the tests get put into their final packaging, complete with a protective cover and a heat spreader to keep them cool. And there you have it, the absolutely incredible journey from a single grain of sand to the very brain of our modern world. It is an amazing testament to what we can do, purifying, printing, and sculpting at a scale that is almost too small to imagine. It really gets you wondering, if this is what we can do today, what on earth will the next generation of these things make possible?